So, all right, so from you just finished lab 4, and that logo from lab 5 on, they'll both be arena-based labs. So in the labs will usually be built on top of an exercise that will come out of the lab textbook from Kelton. Really any version of this textbook from the 3rd edition on should be fine. I've provided copies of the resources you need on Canvas as well. So you can find this at the bookstore, at the library, and again on Canvas, those resources are available. Arena 16.1 is installed on the lab computers, as well as the other lab resources you have available to. For other options for using it at home via either remote access or by downloading it yourself, check out the Arena Downloading and Finding Helpful Examples page on Canvas. The one thing, again, I mentioned this before, Arena 16.1 has a different user interface than the 16.0 and previously, so it may look a little different. The other thing is if installing it yourself, you have to install the Crystal Reports engine manually. I think due to copyright issues, they couldn't automatically install it in this version like they could in previous versions. And there are instructions for doing that in that Canvas page. If you check that out and follow those instructions, you should be able to install that manually. Otherwise, if you're willing to use the new 16.1 interface and find all the blocks that just in a slightly different place, that's great. If you're having trouble with that, you can load the old template panels, and you'll learn how to load template panels in the labs, but I kind of give a little note here that if you right-click on a template panel and you can load additional panels, you'll find an old template panels folder. It'll have all of the old panels that look just like the ones that are in the book. All the same functionalities in the new panels, but just the blocks are in slightly different locations. They apparently focus grouped it and figured out that these were the new panels are easier for people to find the blocks in than the old panels. So supposedly it's an improvement, but you can be the judge of that yourself. Otherwise, homework D2 is due in a week. Homework C1, I think it's still available technically. I forget when its availability window closes, but D2 is technically due in a week, but then its availability window is open for a couple days after that, a standard 4-day penalty grace period, and you can use it as exam practice. So the types of things you'll do in D2 are sort of the most sophisticated things that you'll do on the midterm. ICAF, after ICA E1 is due, which will be due on the E1 lecture, F will be released. It is a much larger ICA. You can take it as many times as you want. It records the highest grade, and it basically randomly samples from previous ICAs. So it's meant to be sort of an online study guide to help you study for the midterm. The other things you can do for studying for the midterm as you're thinking about it is, because the midterm's on Canvas, I've got this little Respondus lockdown browser compliance test that you can take. And that is like a one question, you just check a box. Once you've done it, you'll get access to the midterm module. And you won't get access to the midterm, but you'll be able to get access to a bunch of midterm study materials, including old midterms from previous semesters, including one Canvas-based midterm that you can take as many times as you want as a practice. So those are available once you take that compliance test. Other resources I kind of list here. So as a reminder, the midterm is a 2-stage exam. So there'll be an individual stage in class. Well, you don't have to be in class, you can take it at home, but it'll be during a class period. So when you start it, you'll have a class period to complete it. And you get two-sided hand-produced sheets. And then, but that's all you get. It's otherwise closed book, closed notes, closed collaboration. You have to do it with the respondus and the camera. But then stage 2 is the exact same exam, but you can have open book, open notes, you can collaborate with each other, just as long as you collaborate with people only in this class. So only signed up to take this class this semester in this section. But it'll be exactly the same. You won't get your scores in between, you won't get answers in between. but your total midterm score will be 80% your individual score and 20% your group score. So that's what's coming up there. Again, the, yeah, question? That's, you're all gonna have, I mean, the order, the question orders might be randomized, but it should be, there may be on numerical ones, I can't commit to that because that may randomize it per, like it may give you a random set of parameters, you don't have to calculate it with that. But yeah, it's not like person A is gonna get a qualitatively different exam than person B. And so likewise, when you collaborate, you'll actually have questions that match. Okay. Other questions about the exams? So pause there, or anything else up to this point. Let me make sure there's no questions online. Is stage 2 also online? Stage 1 and 2 are both online. I will be available in this class at this class period if anyone wants to take their stage 1 here with a laptop or their stage 2 here, but both are online. In fact, stage 2, I'm going to give you at least 24 hours to do it. So you'll pretty much when, and I usually give even more time than that. So you'll be able to sort of, you can work on it in the morning, go to classes, work on a little bit in the afternoon, go to classes, whatever, work on it in the evening. It's very flexible. And likewise, stage 1, even though it will be timed, you'll be able to start it within at least a 24-hour window. So once you start it, you got to finish it within a class period. But so if you want to come here and start it, that's fine. But if you want to take off class that day, or say on stage 2, you want to work with people, but you don't want to work in this classroom, then that's fine too. So they're all Canvas-based. They'll all be online. They'll all be graded by Canvas. But we can make use, like we will still burn these lecture periods on the exam for those who would like to use this room for the exam. Hopefully that answers that question. Otherwise, the arena competition, if you're, again, these deadline into September, similar with FlexSim and Simio, and that's all I think I have on announcements. So any questions? Other questions? Pretty clear. All right, for kicks, let's do an attendance question right now, just because we haven't done one this early in a while. If I can find my mouse. There we go. Now if I can find, did it go back up there? I hate it when it goes up there. All right, so I'll put the attendance question link in the chat. And the question is, how many stages is the midterm? Easy question. Okay. So it was how many stages is the midterm? All right, so we've been talking about DES models. We talked about probability last time. Why did we talk about probability? Because DES models capture realistic variation. So there's sim models, they're supposed to be as random as the real world. And what do we mean by as random as the real world? What we mean by that is if we think about the real world, it's really hard to explain the variation that we see in, say, inter-arrival times to an airport. So rather than trying to explicitly model all of that variation, we kind of average it out sort of and turn it into a probabilistic distribution. And just the same way you can simulate realistic outcomes in a board game by rolling a die. So that's what we refer to as the stochastic approach, using randomness as our source of variation. So input modeling is the process of selecting probabilistic models to mimic realistic variation. So like, inter-arrival times, that's one example of it. So that's what we're sort of learning to do, is how to pick those probabilistic models so that even though we have the flow chart for our system that's correct, we need to make sure we also get the randomness that's coming into the flow chart correct. And so in order to do that, we talked last time about how we define probability and probability spaces. So I talked about a probability space has a sample space within it, like this omega, which is a mutually exclusive set of outcomes. An event is a set of those outcomes. So the probability space of the sample space itself is an event that would always happen with probability 1. Probability measure assigns a weight to events. So basically for any set of outcomes, you can assign a probability to them. And the mass of an event is the sum of the mass of all its constituent sub-events or outcomes. So with that, the probability, the probability of any subset of the sample space is going to be greater than or equal to 0, and the probability of the sample space is equal to 1. So that's probability. Then what's a random variable? It's neither random nor a variable. It's a function that maps outcomes from that sample space to the real numbers, referred to as a measurable space. So the probability that x is in between 0 and 5 is actually shorthand for this ugly thing on the right here, which is the probability of the set, so in events, of all outcomes in the sample space for which the random variable x maps those outcomes to numbers between 0 and 5. So this is kind of long and ugly, but this is actually the what we need to make probability work is all of this mechanics over here. But it's a pain to write all that every time, so we simplify it by writing this thing, the probability that x is between 0 and 5. The range of a random variable is the set of all of those numerical values for which there are non-zero probabilities associated with them. So in other words, if all of our outcomes are the sample space omega, the image of omega under the random variable is the range. So we talked about discrete random variables. That's an example where the range are countable. So if we look at all of the real numbers that outcomes associated with, we can count them. And for each element, we might have this shorthand little p of the outcome. And little p here is always going to be greater than or equal to 0. But because it is a probability, it'll also be less than or equal to 1. So all of the outcomes themselves will sum to 1. So we refer to the little p function as the probability mass function, which we'll call the PMF. And we might have a subscript if we have multiple random variables in a discussion at a time. And we'll plot them out using these hairpin-like structures called delta measures. And it doesn't matter too much if you remember it's called a delta measure, but it does matter that you know that when you plot a probability mass function, you do not just use a generic plot that would connect all of them together. It's super important that it has to look kind of like a comb here. It really has to have space in between the outcomes because you're saying that you concentrate mass on each outcome. There's no mass in between the outcomes. And so that's why we have to plot it using this sort of graphical structure here. The other side of that is the continuous random variable, where it's the probability of outcomes that occur on a continuum, so on intervals. And in order for us to characterize that, we have to introduce this ugly thing called probability density, little f, or if I had multiple random variables, little f with the subscript of the random variable, f of x or f y or so on. And so probability density function, this density, if I take the area underneath it, I get probability, but the density itself is not a probability. So if I'm to plot a probability density here, if the actual point right here at x0, that is not a delta measure. So it doesn't have a little hairpin point at the top. So down here, the reason I put a little dot here is I'm indicating that there is mass at that point. There is no mass at a single point here. I can slice this probability density function and say, what is the density at that point? But there is no mass at that point. There is mass in between points A and B. And this is the same way of saying, if I took an infinitesimal slice of a desk, that slice would weigh nothing because it's infinitesimal. But if I took a chunk of a desk, that chunk would weigh something. So that's what we mean by density. So what are the properties of probability density? It's all greater than 0. The area underneath it is equal to 1, but it itself can be greater than 1. And it's equal to 0 if you're outside of the range. So it's a little different than probability mass. So if I look, for example, at these density functions, this is a density function for a uniformly distributed random variable between 0 and 0.5. Because the area under this curve has to be equal to 1, the density goes all the way to 2. Because 2, it's a rectangle. 2 times a half gives me the area under it equal to 1. So the density can be as high as it needs to be for the area to be equal to 1. Similarly, with an exponential, like here, so this is an exponential random variable with a mean of 0.1, and its density goes all the way to 10. So the density does not need to be bounded above by 1. A density can be anything. It's unbounded from above. It can't be any lower than 0. But the area underneath the density, that's the thing that has to be equal to 1. All right, so any questions about that distinction between probability density and probability mass? Or probability. We can call it probability mass, or we can just call it probability, but it's just probability density. Let's check online here. Okay. Great, all right. So for both of those things, both PMFs and PDFs, we have CDFs, which we're going to use a lot for the rest of the course. And you'll see in your homework D2, I think is what the homework is, or D1. And so the cumulative distribution function is defined for any probability measure. It's this function, f of little x, and it's just the probability that the random variable is less than or equal to whatever that argument is, little x. So for probability mass function, you just take all of the outcomes less than or equal to that argument and add up all their probabilities. For a probability density function, you take everything from negative infinity to the argument and you just take the area underneath the curve. And that's how you get your CDF. And so it has really nice properties. So for one, it's non-decreasing. So if you go from A to B, where B is bigger than A, the CDF won't decrease. It always ends at 1 on the right, starts at 0 on the left. And if I'm asked you for the probability of a random variable between A and B, and I give you the CDF, you don't have to do any integration. You just have to evaluate the CDF at the upper interval and evaluate the CDF at the lower interval and subtract, and that gives you the probability. So nice features of CDFs. So the way we use CDFs, kind of relating to what you saw in lab 3, I think, is if you had, let's say, service times of either 3, 6, or 10, where 3 happens 30% of the time, 6, 45% of the time, and 10, 25% of the time, we would like to maybe simulate outcomes. We like to say Excel generate service times 3, 6, or 10 according to this probability mass function in the middle here. And so I'm summarizing again the probability mass function down here. Well, the cumulative function, that tells me all the same information, but it's written in a little bit different way. So if I go to the cumulative function, then I'm saying here that 3 or less happens with a 30% probability, 6 or less happens with a 75% probability, 10 or less happens with a 100% probability. If I know that, I can get the probability mass function out. So I can go from one to the other and back. So as long as I have one, I don't need the other. But in simulation, it turns out the CDF is typically more useful than the PMF. And the reason for that has to do with a convenient way we can draw random numbers, where if we plot the CDF out, so this is that same CDF here. So we can see it's 0 until it hits 3, and then jumps up to 30% until it hits 6, jumps up to 75% until it hits 10, jumps up to 100%, and stays there forever after that. Well, this CDF here, if I were to draw a uniformly distributed random number between 0 and 1 and put it on the y-axis, and then see how the CDF maps it to the x-axis, this process allows me to draw from those three outcomes according to the probability mass function probabilities. So if I draw 100 uniform random variables between 0 and 1, and then I see what outcomes come out of that, 3, 6, and 10 across those 100 trials, then what I will find is that 3 comes out 30% of the time, 6 comes out 45% of the time, and 10 comes out 25% of the time. And what this is sometimes called is the random dart transformation. It's as if you drew this interval, and you had a dart that you threw at a wall, and then you projected down to see where it landed in that interval. And so sometimes your dart might land here and you project down and it hits that point. Sometimes it lands here, you project down and hits that point. If your dart is landing uniformly across this whole point here, or this whole range here, then if you map it down to this region, then the area of these regions corresponds to the probability that the dart has landed in them. And so that's effectively what the CDF does here, is that it takes the y-axis and it turns it into this area division where it sort of creates a dartboard where it's 30% likely that you're going to hit this part of the dartboard. It is 45% likely you'll hit in between this point and here, and it's 25% likely you're going to hit from this point to there. That's the random dart transformation, and it's naturally set up by using the CDF. And we'll learn more about that in lecture E2. But are there questions about this simple example or the CDF? If all of that makes sense so far, all the things I've plotted, can you interpret them and do they make a little bit of sense? Okay. Now we do the same thing for continuous random variables as we learned last time. I take a probability density function like this one here. If I take the area underneath the curve using this formula here, then I will get this expression out here, this kind of purple expression, if I plot, turns into this thing. That's a CDF for an exponential random variable. So up until this point, you've probably started to get a search image for probability density functions for different random variables. That's a bell curve, that's a uniform, that's a triangular. From this point on, you should start building up that search image for CDFs. So when you look at this, you should think that's an exponential. You'll learn how to recognize the CDF for a normal distribution. It won't be a bell curve, right? A CDF for a triangular distribution won't be a triangle, right? But you'll learn how to recognize these as you start looking at these CDFs. And so this is a CDF for an exponential. If I have this CDF, I can do my random dart transformation, but instead of having big regions on the board, now it's like every spot on the dartboard has a different point value. So my darts get thrown from 0 to 1 just as before, but then they get mapped to a continuum of point values from 0 to infinity. And if I draw 100 points here and take a histogram of them, then those 100 points will get spread out in such a way that most of them will cluster up near x is equal to 0. Some of them will land at large values, and I'll end up getting an exponential distribution. So notice that I started with a uniform spacing on the y-axis, but when you project down to the x-axis, it gets stretched out in here, and it gets compressed over here. And that's what sets up, allows me to draw from one distribution and turn it into another distribution. So that's our continuous CDFs and the inverse transform. Any questions about that? Again, we'll talk in more detail about how to do this mathematically in lecture E2, and that's what you'll have practice on in that last homework before the midterm. Questions online? Great. All right, and then the last thing I want to make sure we remember from last time is the subject of moments. So the expected value of a random variable is referred to as the center of mass of a distribution. That's an important moment. And so these are definitions that come right out of your statics class. So right out of a mechanical engineering statics class. So if I think about x is the distance and p is the mass, then we can see that this is just calculating the center of mass, the same way you would calculate center of mass of a bunch of objects positioned on a beam. or I want to say beam, but a bunch of objects positioned on a line. Similarly here, if I have a complex object like a table that exists everywhere, then if I went into the table's center of mass, I can integrate under this, which is the table's density times the position of that point from the end of the table. And that gives me the center of mass of that table. So other names for the expected value are the mean or the first moment. So if I think about my exponential PDF, the mean is right there for this particular exponential. And you should be getting an intuition that if I show you a probability density function, you should be able to have a physical intuition of where the mean will be, because that is exactly where it would balance if you cut that thing out of cardboard and tried to balance it on your finger. So I could have brought, I have an example of this where I've done this, where I've cut these out of cardboard, and I should just keep it in my backpack. And where I can do that and balance it on my finger right at the mean. And so that's where we get there. And it works for discrete as well. So if I have a discrete distribution, if you think of those as dolls of different weights that are sitting on a shelf, then this is the balance point where the heavy doll over here is balanced out by the light doll that has a lot of leverage being farther out over there. And so that's what the mean is. Any outcomes that I add exactly at the mean will not change the mean. So it's kind of like it's exactly like center of mass. If you put a bunch of mass at the center of mass, it doesn't move the center of mass any. So this is what we mean by outliers shifting the mean, is that the closer you put outcomes toward a mean, it's not going to change the mean. But if you throw in an outlier, a very rare case, but it happens, way out here, the distance from in the mean is going to have so much leverage that the distribution with the outlier is going to have a mean that'll be shifted far towards the outlier compared to the distribution without the outlier. That's why we say outliers have statistical leverage. That means that a tiny outcome that is so weird, like so far from the mean, can have the ability of moving the mean towards it the same way a long lever allows a small force to move an object that's very heavy. It's exactly the same process going on there. So that's what we mean by mean. So you should be able to sort of guess where a mean is if you just look at a distribution based on kind of how heavy it looks. We can do higher moments as well. It's the same formula, but we raise the distance or the outcomes to an exponent. And the reason we define those is that there are other useful properties that are easy to be derived from higher order moments, like variance, which measures the spread of a random variable. It has this ugly formula, the expected value of a new random variable created by subtracting off the mean and then squaring the result. Instead of figuring out that expected value of that new random variable, instead, we just take the second moment of our original variable and subtract the square of the mean of our original variable, and we get its variance. And so it allows for an easy way to calculate those things. The standard deviation is just a square root, as you probably all know, and we'll use the symbols sigma and sigma squared to represent standard deviation and variance respectively. I think that's it for the review. So those are the things I really want you to know coming out of probability, pretty much the things down here. Roughly what we mean by outcomes, events, probabilities, what a random variable is, and moments like mean, higher order moments, and variance, and how we interpret mean as kind of a center of mass. So any questions about that before we go into particular distributions that are commonly used when we model? And also check questions online. Okay. All right, so let's look at this guy. So if I, as an exercise for the class and those online, I've got three graphs here, A, B, and C. And so I'd like to know which one's a PDF, which one's a CDF, or which one's neither of those things. So So just take a second and look at that. Things point out here, the shapes of these things, how high they go up. This one goes up to 0.1. This one goes up to 100. This one goes up to 1. This one's always decreasing. This one's always increasing, and it increases to over 100. This one increases, but it's got 0 on one side and 1 on the other. All right, so with that in mind, let's look at, say, A. How many people would think A is, or online, yeah, okay, you can just put in the chat, for example, online, whether you think A is PDF, CDF, or neither. And in class, I just read as a show of hands, how many people think A is a probability density function, PDF? Anybody? How about a CDF? 1 or 2? How about neither? There's a bunch that say neither. Anybody brave enough to say neither, to say why you said neither? What's wrong about this, if anything? I see a couple of PDFs online. Okay, I'll make it easy on this one. This is what I would call a PDF. So why PDF? Well, it's actually hard to know for sure because I don't know the area underneath this curve. But if I say, well, the whole rectangle, it's 100, and on this side it's 0.1, so the whole rectangle has got an area of 10. So I buy that the area underneath this curve is about 1/10 of that. So it seems reasonable to me that the area underneath this curve is equal to 1. All of the y values are greater than 0, and the x values can be anything. So that to me looks to me like a probability density function, or at least if I knew the area underneath it for sure, I could tell, but my best guess is that's probably a probability density function. Any questions on that? Does anybody feel like they disagree, or they really feel like that doesn't meet what you thought which should be a probability density function? All right, online, any comments or? All right, so let's look at B. So if I go down here to B, let's do the same thing. So how many people think B is a probability density function? And then online, you could tell me PDF, CDF, or neither. How many people think B is a cumulative distribution function? A couple of hands. How many think B is neither? It does not belong in probability. All right, let's see online. We got a CDF. All right, so anybody brave enough who said CDF, either online in the chat or in person here, say, why did you think CDF? And I'll give you a hint, you're right. Yeah.
Maybe it's because of the accumulation of probabilities.
So what do you mean by accumulation?
So if there was a 20 that has a certain set of probabilities, but from 20 to 40 it increases, and it gets closer.
Okay, so I think so the comment was it seems like it's an accumulation of probabilities. The way I interpret that is by accumulation is I think you're pointing out that it's always getting larger, but it's always bounded between 0 and 1. Yeah, so it starts at 0, it ends at 1. So that to me is something that's fundamental to a cumulative distribution function. It always starts at 0 and it ends at 1. Now, it could be a probability density function, but if I look at this, I'd say, well, it goes from 0 to 100 and 0 to 1 over here. Well, the area of the whole square is 100. And this is more than half of that square. So there's no way the area underneath this curve is 1. So I'd say it can't be a probability density function, and it otherwise meets all of my everything that I want for a cumulative distribution function. All right, so what about C? How many people think C might be a probability density function? How many people think C might be a cumulative distribution function? What about neither? I see at least the 1 or 2 neithers. Online, I see neithers as well. All right, so C is a little tricky. I know, for one, it can't be a cumulative distribution function, even though it's rising. Can someone here tell me why C can't be a CDF, a cumulative distribution function? What's wrong with it as a CDF? I can also take answers online. I like that. In fact, what's wrong with the fact that it goes up to 100? 0 and 1, right? A CDF, a cumulative distribution function, is a probability. CDFs are probabilities, which means they got to be bounded above by 1. So C can't be a CDF because it goes above 1. So it can't be a CDF. Now, it could conceivably be a probability density function if we make some assumptions about what goes on to the right of this. So if like this were to go down to 0, and we could evaluate the area underneath here, and it was equal to 1, then this could be a probability density function because all of its values are greater than 0, and the area underneath it is equal to 1. But when I actually generated this plot, what I did to generate it was invert B. So it's actually an inverse CDF of an exponential. So this is the PDF of an exponential, this is the CDF of an exponential, and this is the so-called quantile function or inverse CDF of an exponential, which we'll learn a lot more about in the other lecture. But so that's what I want you to get to the point where you can look at these things and say, that's a PDF, that's a CDF, I don't know what that is. Okay, so any questions about those 3 examples? Or online? All right, well, let's take a quick look at another set here. So I'll ask this a little bit differently here. So one of these is a CDF, a cumulative distribution function. So let's try to figure out which one is the cumulative distribution function. So online, if you can put into the chat D, E, F, or G, which one you think is a cumulative distribution. And here, I'll just go through and I'll sort of vote. So how many people think D is the cumulative distribution function? See quite a few hands. How many people think E is the cumulative distribution function? How about F? How about G? All right, so it looks like everybody said D is a cumulative distribution function. Let's see online. We've got D's as well. So that's what I would choose too. Because when I look at D, it goes from 0 to 1. It's non-decreasing. It's always either flat or increasing. And I don't care about what values are in the X outcome, because these are just outcomes. They could be anything, but I do care what the Y is. So that's the CDF there. Actually might be able to do some Zoom magic here. I can, there we go. All right, so D we said is our CDF. Okay. All right, let me do that again. So D is our CDF. Oh, right. So the way I've got this displayed, and you guys, all right, so that's not going to work. All right, so D here is our CDF. There is another one of these, is a probability density function. So if we know D is already off the board, how many people think E is a probability density function? How many people think F is a probability density function? How many think G is probability density function? I got no hands. So let's just try. So I need at least one participant. So how many people think E is a probability density function? All right, I see some hands for E. How many people think F is probability density function? See a couple hands for F. How about G? All right, well, I can tell you, and then online, let's see if we have anybody. I see some E's and some F's online. All right, so for one, okay, I'll tell you, G, it can't be it because it's not even a function, right? So for one value on the x-axis maps to two values on the y-axis. So G is definitely not it. So then I have to look at E and F. Well, E is interesting here, but if I look at its y values, what's wrong with E to be a probability density function just based on the y values? What do we know about probability density functions? They can't be negative, right? So E is maps to negative values here. So it can't be a probability density function. On top of that, the area underneath E, it's not quite clear, but it might be greater than one. It looks like it could be maybe exactly one, because 2 times 1 and then you cut it in half. But but we have to make a lot of assumptions what would happen out here. But either way, it's negative, so that's not going to work. So process of elimination, it must be F. And that makes sense because F is it's greater than 0 everywhere. It can go larger than 1. That's totally okay for density. And if I were to sort of estimate the area underneath this curve, well, there's 4 times 1.5 is about 6. And so I could say, well, this, it's hard to say if that's exactly a sixth of the area, but it's thin up top and down here. I bet if I were to like turn this into a rectangle, it'd be about a strip of a sixth wide. So it kind of makes sense to me. The area underneath there is roughly equal to 1. So that's our CDF. That's our PDF. And then if I look more closely, this thing here is the inverse of the CDF. So I just flipped it over the diagonal. And this is the inverse of a PDF, which isn't anything. That, like I said, it's not even a function. You can only do it graphically. So, so that's it. So PDF, inverse CDF, which we haven't really learned yet. I'm sorry, PDF, CDF, inverse CDF. So those are the 3 that we work here: PDF, CDF, inverse CDF. So any questions about that? And I guess neither would be the answer for down here. All right. And I see online, probabilities can't be negative. So that's, yeah, that was our solution there. All right, great. Okay, so looking forward, so we're gonna, for the rest of the day, we're gonna talk about some common models and how we use them for different real world phenomena. So when you go into Arena and start building the models, then when it asks you for what probabilistic model to put in there, we gotta know how to choose. And so this is where we're starting to build up that vocabulary. Then the next lecture, we're going to talk about how to generate uniformly distributed random numbers. That's like your homework C. And then in the lecture after that, how to use the numbers we've generated to generate arbitrary random variables like the ones we're talking about here today. And then that brings us to the end of the content pre-midterm. So we'll have the midterm review lecture, and then we'll have the 2-stage exams after that. So that's the plan kind of going forward here. All right, so any questions about that before we knock out the rest of today? Any questions online? Okay. All right, so like I was saying, that we use a stochastic approach, which means we're going to choose probabilistic models that mimic variation. We call those probabilistic models input models. So we think of the realistic input models as going into our simulation logic and producing realistic outputs. But if we get the wrong inputs, we're going to get bad outputs. So it's the garbage in, garbage out property. Now, there are a few fundamental over your career. If you do a lot of stochastic modeling and simulation, these will be your kind of go-to models. So on the continuous side, it's kind of this list. On the discrete side, it's this list. And then based on your field, you might go into some others, but these will be like the first ones that come up and pop into your mind. So over your career, you build up familiarity with all of these. In this class, we're going to start with the bold ones in this list and not worry about the gray ones. But note that the ones that we talk about in this list that are bolded, they're very useful, but they certainly aren't, there certainly are a case for these other ones like beta, log normal, gamma, Pareto, and Rayleigh that that you'll see a lot, but they're a little more advanced for this class. But I'm just trying to say that this class is not going to cover everything that you would use if you were to go out in industry and start doing stochastic simulation, but it's easy to pick up these other ones, and you'll definitely need these to begin with. And so this is our starter pack of probabilistic models for input modeling. So today I just want to go through a couple of these and say, why would we pick one over the other? Because sometimes we can apply multiple, so why do we pick one over another if we don't really have any other apparent reasons for doing so? And so the first one we start with is the uniform distribution, which in homework C, you've had a little bit of exposure to. So this is a continuous random variable that's distributed between a lower bound and an upper bound. So I guess you've also seen this in lab 3. And so its probability density function looks like a boxcar, and its cumulative distribution function looks like a ramp. And so the slope of this ramp relates to the range of this random variable. And so that's what we see here is the probability density function. It's got a constant across this range, which allows the area underneath here to be exactly equal to 1. And that kind of slope, 1 minus b over a, that is what sets the slope of this ramp, 1 minus b over a here. Now, you use uniform distributions kind of like when somebody gives you bounds, a and b, and that's all they give you. So you have no reason that any particular outcome in between a and b should be any more often drawn than any of the other ones. So they just say that we know that the arrival time for this particular event is not going to be any earlier than A and any later than B, but otherwise we have no information. And this is what we refer to as a maximum entropy distribution. And what I mean by that is if you give those constraints, A and B, you could pick a bunch of other ways to distribute your probabilities in between them. But each one of those adds additional information. And if we want to minimize the information, and we can measure information with this property called entropy, if we want to minimize information stored in the distribution, we choose what's called the maximal entropy distribution subject to those constraints. And for the constraints that it's no less than A and no greater than B, and that's it, this is the best distribution. That's the maximal entropy distribution. So the properties of this, its mean is right in the middle of its range. Its variance is this formula here. And what's really nice about it is the probability of an interval is proportional to its length. So if your interval is half the range, it occurs with 50% probability. So you take the length of the interval, you divide by the range, and that's the probability that interval will happen. So being able to generate uniform random numbers between 0 and 1 allows us to generate any other random variable, as we'll talk about in lectures E1 and E2. So that's the uniform, sort of a go-to if you have very little information, just a lower bound and an upper bound. Now, sometimes they come at you and they say, well, we know it'll be no lower than A, we know it'll be no higher than B, but we do tend to see outcomes that are closer to some midpoint. And so if you have no other information than that, you don't know the average, you just know that there's a mode that, it's more likely to have this particular intermediate outcome, but then you've got bounds. Then you use a triangular distribution. And there's not a really good mathematical justification for ever using the triangular distribution. It's what we refer to as kind of an empirical distribution, kind of like if you've given me information, but I have no way to mathematically encode it. And so this is my best model for you saying if there's a mode in between this limited range. So this is the kind of ugly formula for its density function. If you integrate, this is its cumulative distribution function. And since the density function are two ramps, then it should make sense that the CDF looks like a quadratic with an inflection point and then another quadratic. So as you see quadratics, and especially when they've got inflection points and they flip and become the quadratic that's bending in the other direction, then you've probably looked at the CDF for a triangular. So triangular CDFs have this nice kind of inflection point type look to them. All right. So any questions about those two kind of empirical distributions, uniform and triangular? Nothing really special there. Just you're given bounds and maybe some information about intermediate modes. Somebody asked online, so the CDF y-axis has to be 0 to 1. So sorry to miss that question there. Yes, on a CDF, the y-axis should always be from 0 to 1. It will always eventually hit 1 on the right, and it will always eventually hit 0 on the left. Okay. All right, now normal distribution. This is a beautiful distribution. It's symmetric. It's described by this density function. Integrate that, which is very difficult to do, and get a function, get an actual formula out of there. But then you end up getting something that looks like this. So a normal distribution is good when someone says these values are, we have no reason to bound these values, which often means they're either very, very large, so we don't have to worry about negative numbers, or they can be negative. And they've given you a known mean. So if you say they're unbounded and they have a known mean, the maximal entropy distribution is, or the least unbiased distribution, is the bell curve, is the normal distribution. So if somebody just gives you a mean, basically, and no bounds, go with the normal. Or they give you a mean, and that mean is extremely large, so you don't have to worry about negative numbers, you go with the normal. And so then you also have to give you some variance. So that's the thing. I need to give you a mean and some variance that makes you feel like that the outcomes will never come into the negatives if it's something that negative numbers don't mean anything, or if you're okay with negative numbers and they've given you a mean and a variance, you go with the normal. So it's the distribution, the best distribution when you know where it's centered and how it's dispersed, and you're not worried about bounds because it's supported everywhere. You theoretically could get outcomes at positive infinity or at negative infinity. So I've mentioned before, it's also the output of the central limit theorem. So if you are asked to model an additive process, so this might be making a submarine sandwich, you know, it's got a bunch of steps and each one of our independent random steps. You want to model the whole process added together. Or you're trying to model how much wear something gets when it's used over and over and over again. Then you go with a normal distribution because those additive processes tend to produce in their sum bell curves. And so that's what we use normal distributions for. All right, any questions about the things I meant here about the normal? So mean and variance are given. It's a good one for the normal, just be careful about negative numbers. And it's good for additive processes. All right, questions online about any of this? Okay. All right, so just going through this list, again, this is just a vocabulary that we end up building up. An exponential. So an exponential is one that's bounded from below. It's never any lower than 0, or it can be shifted, of course, but nominally no lower than 0. And it's otherwise is semi-infinite. So it can go to infinity on the other side of it. So it's really good for when somebody says, this is something that's non-negative and I have a known mean, and that's all they've given you. So if all you know is the mean and that it's non-negative, this is the maximal entropy, least unbiased distribution. So there's a lot of different ways you could deal with it. So he says, this thing is, you know, it's timing. And so we know that on average, it happens every 15 minutes. And because it's time, it's non-negative. Well, you could come up with a bunch of different distributions that are non-negative that have a mean of 15. But if they've given you no other information, you should use the exponential. The exponential is the I don't know anything else but the mean distribution. And so there are good mathematical reasons for that. And so oftentimes we talk about the mean of the exponential in terms of its reciprocal, which we refer to as the rate. So we can talk about an exponential rate, and we can also talk about the exponential's mean, and they're just reciprocals of each other. The standard deviation, so the mean of an exponential is 1 over its rate, and so is its standard deviation. So that's one of the interesting things about the mean is in one parameter, you get both the mean and the standard deviation. Of course, the variance then would be the square of that. So an example of that, waiting time until a random failure with a known rate. And so if you know that on average light bulbs burn out once every 6 months, then you might model the time until that failure with an exponential distribution, and that exponential distribution will have an average of 6 months. So that's an example of one of the things that we make. So a lot of failure times and waiting times we can model nominally with an exponential until someone gives us more information. So it's our go-to when you've only given us a mean. There's any questions about that? Do you understand what I mean by only given a mean? It has to be non-negative and so on. So there's a question online. Will we need to memorize CDF and PDF formulas for each distribution? No. If a formula matters on a midterm, I'll give you that formula. I should say for things like uniform and triangular, you should be able to draw those. And if you can draw those because they're so simple, I think you should be able to kind of figure out what the formulas are. You should be able to recognize the graphs for these, but you don't need to memorize the PDFs and CDFs. If those are important to a question, I'll give them to you. Okay. So there's a lot of useful properties to the exponential, which is one of the reasons why it's used so much. So for when you take 470, you'll learn about queuing networks and Kendall's notation, and you'll learn that queuing nodes are categorized by the interarrival time to the nodes, the service time distribution at the nodes, and the number of servers. And the M that is used in Kendall's notation to characterize a queuing node stands for memoryless or Markovian. And that memoryless actually comes from the exponential. So this is a property you need to remember that exponentials have. The memorylessness of the exponential means that the amount of time you've waited for an exponential does not give you any time of how much more time you will wait until an event happens. Written mathematically, it's saying the probability that the exponential is greater than x plus y, given that it's already greater than x, is equal to the probability that it's greater than y. So, as I've said down here, just saying that in words, if I've already operated for 5 minutes, the probability the machine will die at 8 is equal to the probability then the machine will die at 3. So you don't get anything out of knowing how long you've waited for a failure. So if I know that a light bulb fails every 6 months, now in reality this breaks down. But if I were to think about, if I were to walk into a room, knowing how long the light bulb has been installed doesn't tell me exactly how long I'm going to wait. So even if the light bulb's been installed for 3 months, I still have to assume that I've got the entire sort of exponential distribution from that point on. So that's what I mean, it has no memory. If it's an exponential now, it's the exact same exponential later, even though you know you've been waiting. That's just due to the shape of the distribution. It's very different than like waiting for a bus. If you're modeling waiting for a bus, you should never model that with an exponential. Because if you wait for a bus, you know that a bus comes every roughly 15 minutes, plus or minus a little bit. It's not an exponential distribution. So if you see a bunch of people waiting at the bus stop who've waited there for a long amount of time, you know the bus is probably about to come. And so knowing how long people have waited tells you how much more time is left to wait for the bus. So never model a bus interarrival time with an exponential, because definitely the bus stop does not have this property. So things that you model with exponentials automatically get this property. Things that don't have this property in nature should not be modeled with an exponential. So any questions on what I mean by memorylessness? Questions online? Okay. All right, almost through these. We can now build other random variables out of an exponential. And the first one that's derived from an exponential is the Erlang distribution, sometimes called the Erlang-k distribution. And it's just the sum of k exponentials. So if I know that, let's say, for example, I've got 6 light bulbs in this cabinet here, And ASU wants to know, when do they need to send somebody out to put more light bulbs in this cabinet, and light bulbs for some light that somebody like that I could replace whenever I come in. Well, if I know that each light bulb has an exponential failure time, then the time it takes to burn out all 6 in a sequence is going to be an Erlang-6 distribution, because all light bulbs are identical, and we wait for one failure before we start the clock on the next failure and the next failure and the next failure. So it is the sum of k independent exponential variables. And so an Erlang-1 is exactly an exponential. So this k equals 1 up here is an exponential. It just degenerates into just an exponential. An Erlang-2, that's this kind of orangish line, now is a little bit more hump shaped. And so because it's a sum, we should not be surprised that as k gets larger, like in this blue one, k equals 9, it's almost a symmetric curve. It gets more and more hump shaped and more symmetric. Can anyone guess, if I take k to infinity, what is the limiting distribution of this density function? And remember, it's a sum. So I've said it before, like additive processes. So typically when things add up, when you add up independent random variables, they become shaped like what distribution? Central limit theorem, a normal distribution. So if you take this function and take k to infinity, you will get the PDF for an exponential, or sorry, for a normal distribution out. Likewise, if you took this CDF and took k to infinity, you would get a normal distribution CDF out. And so if you look at these humps, as k gets larger and larger, this becomes looking more and more like a normal distribution. So if you know that it's definitely formed by exponentials, this will be the better distribution to use, because it will match kind of sooner. But as k gets really large, then these basically turn into normal distributions anyway, and you may as well use a normal. All right, so any questions about the Erlang? It's just a sum of k exponentials. And I see normal online. Thank you for that. Okay. Now the failure people, also like reliability engineers, will often use a Weibull distribution. And a Weibull distribution is also meant to be a generalization of an exponential. So this Weibull distribution, it has a scale parameter, which is like the mean of an exponential, as well as a shape parameter k, similar to the Erlang distribution. And if k is equal to 1, a Weibull is an exponential, the same as the Erlang. But otherwise, k is a generic parameter that allows you to bend an exponential into different shapes. So if I'm to look at some of these examples here, this k equals 1 is this kind of orange line, the second line down here. So it's this one, it looks very exponential. This blue one up top, that's k equals 0.5, and notice it's kind of like a ski slope. So it's like the exponential has been pulled in so that all of the outcomes happen way up front, at very low times, and then only a few of the outcomes happen at very late times. If I pull k the other way, like this red line, this magenta line here is k equals 1.5, and this green line here is k equals 5. As k gets larger, then the exponential gets bent in the other direction, and it even starts looking kind of hump-shaped. So it concentrates all of the failures, if we're thinking about failure distributions, later on in life. And so a Weibull distribution allows us to sort of say that, well, our product acts like an exponential, either early in its life or late in its life, but it has maybe too many failures early to really be an exponential, or it has too many failures late at a particular time to really act like an exponential. So a Weibull distribution helps us take an exponential, which is like the nominal, like perfect idealized failure distribution, and bend it into empirical distributions matching failure laws that we actually see in reality. So for those of you who've taken a reliability engineering course, you might have heard of bathtub plots. And bathtub plots effectively plot these shaped parameters for these Weibull distributions. And so they have to do with, if we're modeling a product, how often is it going to fail, early, late, and so on, and how do different products differ. And the Weibull gives us a very flexible distribution to say whether things are going to fail late in life or early in life, or are they going to actually behave like a real exponential where you just kind of take it to k equals 1 and the Weibull disappears and it becomes just an exponential. So it's a very good, very generic failure time distribution, but there's no mathematical insight behind it. It's just a good flexible failure time distribution. Okay. All right. Questions about that? Erlang and Weibull, kind of exponential cousins. The other exponential friend that is we need to talk about is discrete, and that's the Poisson distribution. And a lot of students confuse the Poisson and the exponential because they're so related. But Poisson is discrete, it's a count. An exponential is continuous, it's an actual, like it's a waiting time. So what is a Poisson? A Poisson represents the number of events occurring in a fixed interval of time if the interarrival times are basically exponentially distributed. So if I were to count, if I had a bunch of exponential interarrival times, so like I get one arrival per minute, then I were to count how many arrivals I got over an hour, then if all of those interarrivals were exponentially distributed, then the count of how many actually arrive in an hour would be Poisson distributed. So that's why it's got these little dots here. And I think Wikipedia did the thing that I don't like, and they connected all the lines here. But I like that they put the solid dots, showing you that you should only interpret them where the dots are. And so we can see here that these are distributed not continuously, but over the integers. So they're the number of events that occur whose interarrivals are exponentially distributed. So Poisson has a rate parameter, which is, we call here alpha. Sometimes it's called lambda. And the way we interpret that alpha is it's basically the underlying exponential's rate, lambda, times the length of the interval t. So if it's a 60-minute interval t and they arrive 1 per minute, then I'd say, well, 1 per minute times 60 minutes means that an average of 60 will arrive. And that's what I would parameterize that. So if I know that 1 per minute arriving, and I just need to know how many arrive in an hour, then I draw from a Poisson with an average of 60. So that's a way that I don't have to actually simulate all 60 arrivals. I can just simulate the count of the arrivals, and that's what the Poisson is. Questions about that? All right, so with that, what I think I'm going to do is the other 4 that I want to cover here, Bernoulli binomial, negative binomial, and the Poisson process, I'm going to just start on Thursday's lecture because aside from the Poisson process, they are not exponential related. So we'll kind of look into that family there. So let me just short circuit to an attendance exercise. And the next one that I had here, probably in between. All right, so there. So I'll give you your final attendance question for today. And the question is, what distribution should you use if you know the variable is non-negative and has a given mean, but no other information? So you're only given the fact that it's non-negative and it has a known mean, and that's it. Which distribution that we've talked about should you use to model that process? And otherwise, that's all I've got for you today. So I will see you on Thursday. We'll wrap up this and start the random number generation stuff, if I got my timing right.
What was the number again?
Mean, it's non-negative, so it's 0 to infinity, and the mean is known, and that's it. Any questions left online? If not, that's all I've got for you, and we'll see you Thursday.